recorded
That
just
is
started.
perfect. Yeah. And so just FYI, we give like few minutes for everyone to join. That's why if we can just hold for a couple of more minutes, start at 1:05, that would be
Sure,
wonderful.
Yep,
sure.
Yeah,
yep, that's fine.
thank you. Um,
And Hossein, as the host, I do not know if I can see the questions at the end or not. If
um,
not, is somebody who
so
can,
this
because
is
we did it
interesting.
last semester, it didn't work on my end.
Right. So I do see the chat, and I
Okay.
ask everyone in the audience to please put your question in the chat box. I know there's a Q&A tab separately, but it's interesting that I don't see that myself here. So perhaps,
Same here. I don't see it, but I guess I can see the chat box.
yeah, well, I do
Yeah.
have, so I figured it out. So next to the
Sure.
chat, those three dots,
Uh-huh,
Lisa,
uh-huh.
those three dots, you
Yes,
click on
yes,
it,
yeah,
then
yeah,
Q&A appears there too.
yes.
So
I'm still behind in technology. Yes, I found it.
yeah, just same for all of us.
Yeah,
So
yeah,
yes,
yeah.
like to basically everyone to put their questions either way in the chat or Q&A. And if you'd like to basically uh, ask it yourself, we can simply unmute you in order to do that. And Mason, would you like to do the introduction?
Sure. Yeah, I can make it quick and short in the interest of time. Okay, good afternoon, everyone, ladies and gentlemen, students and colleagues, faculties. It's my great pleasure to welcome Dr. William Mars to our graduate seminar series. I briefly go through some statements in this bio that I have in front of me. Dr. Mars earned his honors bachelor's degree with polymer specialization at University of Akron. Then he moved to University of Toledo and got his master's and PhD at University of Toledo, Department of Mechanical Engineering, and interestingly, laboratory of fatigue with my colleague, Dr. Ali Fatemi, who is now at University of Memphis. Dr. Mars is also the author of Endurica Fatigue Life Solver, which is the world's first commercially available simulation for fatigue analysis of rubber. He's also the founder and president of Endurica LLC. And I add one more statement here that he has published a great number of reviewed papers, more than 50 peer-reviewed journal publications, plus 4 patents. With that being said, and without further ado, yeah, I give this stage to you, Will, and we have some question and answer at the end of your talk. Thank you so much.
Thank you for the invitation to speak, Professor Hagshenis, and it's a great honor to be here. You know, I'm a rocket. Did my PhD, finished it in 2001 with Professor Ali Fatimi's group. So yeah, hopefully you can all see my screen. You know, I thought what might be interesting to talk about today. Yeah, I guess I can certainly tell you a little bit about you know, what happened to me after I got my PhD, uh, and I thought this would also be an interesting topic, which is approaches for aligning an engineering budget with durability requirements in rubber part design. Now, the rubber part design, that's kind of, you know, when um, that ended up being my specialty. That's kind of Endurica's superpower is specifically rubber and durability. Um, but aligning an engineering budget with requirements, that's something that probably all of us at some point in our careers are going to have to do. I don't care where you are, you're always going to have a boss, and you're always going to have a budget, and you're always going to have to um, what I mean, you know, work to align the um, uh, the job that needs doing with the resources that you've got. And so we'll, like I say, we'll talk about what that looks like in my world, and hopefully you'll be able to carry away something that's useful to you down the road somewhere. All right. Yeah, so a little bit about my journey. Yeah, I finished my PhD in 2001. My PhD thesis topic was multi-axial fatigue of rubber. Um, and I when I finished my PhD, um, uh, we, uh, we obviously published you know, a few papers, and those papers really were kind of the seeds that sort of led to everything else later. Um, and Immediately after, well, during and after my PhD, I worked for a company in Findlay, Ohio here, Cooper Tire and Rubber Company, um, which was recently bought out by Goodyear. Um, and that was obviously after my time, but yeah, so in 2001, when I finished my PhD, I went into, I was in a research group at Cooper Tire, working on finite elements of tires and working on experimental mechanics for tire materials, cords and rubber. Um, and So what happened with the papers that we published was that they kind of took on a life of their own. I think we published maybe, I don't know, 7 or 8 papers. Um, and people started reading them and citing them, and by the time 2008 came around, um, sort of a unique opportunity arose in which the Army put out a call for proposals, and they were looking for a capability to predict fatigue performance in rubber tank track pad, you know, the ground pad on the track system, and and that when they wrote that sort of call for proposals, they cited 3 papers, and I had written 2 of them. Uh, so at that point, I wrote a proposal, and they funded it, and that was the first 3 years of Endurica. So I jumped off in 2008 to when I was awarded the contract. One of the conditions of receiving that was that I give up my comfortable corporate job and that I start my own thing. And so that's what I did. I did talk to my wife first. She agreed to come with me on this journey, and courageously, I might add. um, Yeah, so in 2008, I started off, it was just me in my dining room, and then for the first 3 years, our customer was the Army, and we used that time to develop a commercial code. Um, the game was always, by the end of the 3 years, to have hopefully other customers that would be buying the code and you know, keep it as an ongoing concern, and that's pretty much what happened. And so this is what, year number 14 for us. Our company, we've grown from just me to these days we are in total 7 people. 2 of us are PhDs. 4 of us are mechanical engineers. We've got a marketing person. We've got a person who's, you know, really good at doing the accounting types of things. Yeah, and we are laser beam focused on helping other companies to get durability right for rubber products. So anybody who makes a rubber thing that has a durability requirement, we make tools and workflows and experimental procedures that they can use to you know, to model pretty much any aspect of durability and make sure that when they do the design that they're doing it right. So that's what we do. Here's a little cartoon that sort of talks about, well, so in the first panel, the boss comes to the engineer and he says, "Hey, look, you've got in 6 months, we're going to launch our next product release, and so get to work and get that, you know, get that thing ready to go." So the engineer goes off and lays out a schedule of things that needs doing, and he puts together all of the specs and models and geometry and so forth, materials, and 5 months later, he's got a prototype. And once you have a prototype, then it comes time to go and test that prototype. And so you take it to the testing department, and of course the testing guys are always good at breaking things, because that's their job, and so they do, and then everybody has a meeting and they talk about why the thing failed. And the people in a typical rubber company, you've got two large groups. You've got one group that's responsible for the material, right, the recipe and the rubber compound. You've got other groups that are responsible for the design of the product. And so the materials guys will say, oh, you need to make the product better. And the product guys will say, oh, we need better materials to work with. And, somebody will say, oh, it's the design, it's the process in the factory. And everybody's pointing fingers. And, and so now everybody has ideas, coulda, woulda, shoulda. So where we want to get to is a workplace culture of get the design right the first time. And how do you do that? Well, what you need to be able to do is bring all this. You still have to do the test, but you need to all of the design decisions that are going to affect the performance of the test. You need to be able to simulate those up front, so that you can get those decisions right, get those material selections, get the loads, get all that stuff right the first time. Because otherwise, when you get to this meeting, now you have to go back and do another iteration, and that's expensive, and nobody likes that. So anyhow, you don't want to be in the coulda, woulda, shoulda, right? You want to get it right the first time. Now, the other real world experience, I guess, is that every project that you're ever going to have is going to come with limits, right? And I just picked off some funny cartoons from the internet here that kind of illustrate this, right? Your client, expectations and versus your client budget. What kind of weapon do you bring to what kind of situation? It's important to bring the right tools to the right situation, let's say. And of course, your boss is always going to, there's always going to be a deadline where, if it takes you longer to do the development than the schedule allows for, there's going to be problems. So so the question is well, how do you go about sort of aligning the objectives that you have in a development program against against the activities that you need to do, the kinds of analyses, the kinds of testing that you need to do, and what I want to say is, hey, in fatigue design, there's a huge range of tools in the toolbox, and so we need to think about the design intent and the requirements. That's basically going to be your budget and your deadline, right? And it's going to be the functional specification on what your product needs to do, and then we can break this down further into what are we going to do from the perspective of describing the behavior of the materials. One thing about rubber that not everybody appreciates is that it's not like steel where you can just look in the back of the book and get the material properties for rubber. With rubber, rubber is more like fine French cooking. Every plate that's served is a very unique recipe, and the material properties of the rubber are very highly customizable, right? You can have very hard rubbers, very soft rubbers, strong rubbers, weak rubbers, rubbers that are resistant to, in tires, they worry about whether gases can permeate through the rubber. They worry about abrasion. There's a whole long list of different parameters, and because you can customize the polymer type and the ingredients of the recipe for making the rubber, you can end up with a huge range of materials. So characterizing the behavior of the material becomes a very important part of what you need to do in these projects. Also, and of course, what you do is also going to depend on how much time you have and how much budget you have. Sometimes you're in a situation where the boss says, "Give me an answer tomorrow," and you don't have time to measure anything. So how do you respond in that situation? Other times, somebody's going to come to you and say, "Look, we're doing a moonshot here, and it has to be right. And you can spend as much money as you want, but get it right." And then there's all sorts of in-between situations. Same sort of considerations on the analysis side, right? We're going to need to think about what kind of analysis do we have time to do, and so which features of the problem do we bring in, which features of the problems do we make assumptions about. So in order to organize our thinking about this, it's helpful to bring in a framework that if you read any, I think, fatigue textbook, they'll talk about this framework. But it's a very useful framework for organizing your activity around how to align your budget and your project goals. So I guess the first thing to do is say, well, hey, we can break this down into 4 different philosophical approaches or sets of, these are different ways of specifying the durability requirements. And the very simplest way, so there's 4 of them. There's one that we call infinite life, there's one that we call safe life, there's one that we're going to call damage tolerant, and there's one that we call fail safe. Now, the simplest one is the infinite life approach. And in the infinite life approach, what we say is, hey, look, when we design this thing, we are not going to allow for the possibility of damage. And so what we'll do is in order to use this approach, we need to know, first of all, what's the fatigue limit of the rubber, right? There's some load below which, if you keep the load below a certain limit, then cracks don't grow ever. Now, in order to apply this, you need to know what that limit is, and you also need to know C naught. So C naught is the crack precursor size, right? All materials contain initial cracks in the microstructure, and so if you're working with rubber, and if you know this fatigue limit, if you know the precursor size, that puts you in a position to calculate basically a crack driving force, right? An energy, if you've taken fracture mechanics, energy release rate is what we use. And you can compare your energy release rate to that fatigue limit. And if your driving force on the crack is below the fatigue limit, then you have infinite life. And you can calculate this safety factor S, right? It says, hey, I've got a margin of 2 times relative to infinite life, or I've got a margin of 10 times, and then you're done. And like I say, cheap approach, because you only need to test one or 2 things. Your finite element model, only needs to look at the worst case loadings, and what you end up with is just this simple measure S. Now, this does not tell you if when you do the analysis you find out that S is less than 1, right? That means that the life is not infinite. And in that case, this analysis will not tell you how long the part might last. And if you do the calculation and find that S is less than 1, that means if you want to answer that question, you have to go up to the next level, which is the safe life approach, right? In the safe life approach, we say, hey, look, this product has to endure for a certain number of cycles or a certain time period under certain conditions. And so when we do our design, we are going to we're going to make predictions of the life based on these loads, and we're going to check that the design lasts at least that long. It doesn't have to live forever, but it has to last at least as long as what we calculate using a safe life approach. Now, the safe life approach gets more complicated because suddenly it's not just a matter of checking whether we're above or below a certain line. Now it becomes a matter of, well, is the crack growing? How fast is it growing? Um, and so now you have to sort of, uh, get a lot more complicated in describing the material behavior. You have to describe stress strain behavior. You have to describe fatigue limit. You have to describe crack growth rate law. There's other effects: temperature dependence, rate dependence, strain crystallization. You start getting into all the things that make rubber very unique. Um, but we can, if you give me a load case, I can predict how many repeats of that load case, and I can compare it to my requirement, and that's the safe life approach. Now, where the safe life approach starts to hit a barrier is when you start to say, well, I don't just have a single load case, I've got 10 load cases, right? Load case one happens, load case one happens 1,000,000 times, load case two happens 100 times, load case three happens 30 times. And you can sort of think of a schedule, or you could sort of say, well, every single day the product sees a different type of loading. And so in that case, we need to start thinking along the lines of damage tolerance. And in this case, what we're going to say is that, hey, if we acknowledge the fact that the structure has a crack in it, and we say, well, if the crack has that crack, what does this load case do to the growth of that crack over a certain increment of time? And how do I sort of monitor that? How do I inspect? And if I have a given crack state, how do I go from there and predict the future based on some assumed future loading, right? That's what we call the damage tolerant approach. And then finally, the last approach is what we'll call fail safe. And in this case, what you say is, hey, look, inevitably the part is going to fail. So how do I take care such that in the design of the part, when it fails, it's going to do that in a way that's safe for people, right? And in a way that's convenient, convenient for how we do operations or maintenance or management or whatever, right? And so things you would do here is maybe you would build redundancy, right? You have a second load path. So if the part fails, the load is taken up somewhere else. You have a weak link, sort of a mechanical fuse type idea, right? So that if the part breaks, things shut down safely. Monitoring and detection of defects can also be a thing here, right? And this is an application where we would start talking about, I don't know if anyone here has heard of a digital twin, but the idea is that you can have a model, think of a dashboard that corresponds to your part. And if you're continuously reading off the loads and the displacements, you can, in principle, track the development of damage through every single thing that happens in real life. And then your maintenance people will have a sort of warning when things are about to go bad before it happens. We can predict, right? It's called predictive maintenance, right? So that kind of falls in the category of this fail-safe approach. Obviously, there's a lot of sophistication here in terms of how you measure things, how you stream those measurements, how you do the how you update and communicate calculations to the stakeholders that need to receive it. But anyhow, so in a sense, this is maybe the most sophisticated and expensive approach. Although it can be pretty simple to provide a second load path. But yeah, so these are some approaches that we can use to do this. Now in rubber, I'll just briefly, one of the things that makes rubber different from metal in terms of fatigue parameters is material behavior. And so, like I say, you sort of have to think about, you sort of have to sort the material behavior into categories of, well, there's some things that you always need to know for every single analysis you might ever do. And there's other things that maybe you only need to know in certain applications, right? So for sure, the basic mechanical behavior that we would always want to know is, we're always going to want to know stress strain behavior. So, in rubber, we're very concerned with the nonlinear elastic properties of the rubber. So, So we use hyperelasticity. We're concerned with steady state cyclic behavior when we're working with fatigue. We're also concerned with what I call the core fatigue behaviors. So basically that would consist of a crack growth rate curve, and it would consist of a crack nucleation curve. So we do both of those kinds of experiments in order to prepare for doing analysis, and that's kind of the basic level. And then on top of that, you can add what I would say is common behavior, but you don't always have to think about these things. Sometimes in certain applications, the thermal dependence, rubber can, if you cycle it fast, it can self-heat. And so sometimes you have to think about that. Sometimes you have to think about the dependence of the crack growth rate law on temperature. So those are things that can be characterized. Under certain conditions, some rubbers will exhibit an effect known as strain crystallization, which results in a strong mean stress benefit. So in certain rubbers, if they crystallize, if you increase the mean stress, that promotes crystallization, which in turn increases the fatigue life of the rubber. It's kind of a mind blow. I know people who do metal fatigue always think that if you increase mean stresses, that's bad. For rubber, that's not always true. Sometimes it's like that, but if you've got crystallization, there are conditions where you can benefit from this. And so if that's the case, then you would need to characterize that. We measure, in cases where we have very long fatigue life, it becomes important to know what that fatigue limit is. We can also look at cyclic softening, which is when you cycle rubber, the stress strain curve gets softer and softer gradually over time. We can look at aging, where with a heat exposure, the rubber might embrittle, right? So if you can imagine taking a piece of rubber and putting it down in Texas or Arizona, over time, the material will become more brittle, it'll become weak. And in a fatigue analysis, sometimes we want to take account of that. We can look at creep effects, we can look at reliability. These are all different effects that you might think about. Now, would you always include every single test? No, that would be very expensive. But so you might start off with the basics, and then depending on the objectives and the budget, you might add these other things in as part of your study of how the material behaves. Now here's a list of what material characterizations you might do in each of these categories, right? So I've color coded these. Things that are green are kind of like bare minimum. Things that are yellow are things that you could add as sort of an advanced, at an advanced level. So, for infinite life, you need to know stress strain behavior and intrinsic strength. And maybe if you want to add to that, you could also look at reliability. If you're doing a safe life type of analysis, you're going to have to know more about the material. So here we need not just the fatigue limit, but we also need now the crack growth rate curve, the crack nucleation curve, and then maybe some of these other effects, right? Thermal effects, crystallization effects, creep, for doing safe life. If we're going to do damage tolerant, now maybe we have to take into account the cyclic softening, because the material is going to get softer, which means I have to recompute my stresses and strains on some kind of incremental basis, right? Every 100,000 cycles, I have to update my final model to reflect the fact that the stress strain curves have become softer. And yeah, so you can sort of see how these different characterizations get more complicated and scale up as you adopt more and more sophistication into your analysis. So now, as far as, now that was just materials testing, we also have to think about analysis tools. And of course, if you're doing this kind of work, you're probably using a finite element solver like Abacus or ANSYS or MSC Mark. Those are not our tools. Our tools are these tools here, CL, DT, and EIE. Those are the Endurica software products. And each of these tools has a different workflow. The CL workflow is the workflow that we use if you give me a duty cycle, and if you ask me how many repeats of that single load case can the part endure, that's the situation where I'll use the CL solver. It was the very first solver that we wrote. and so that's kind of the basic tool set. The next one is our incremental solver, and we call it DT. It should make you think of like an increment of time, right? Delta T. This is the workflow that we would use when we have to accrue damage across different load cases, right? With CL, I can only have a single load case. With DT, I can make a schedule of cases, and I can accrue damage as you go further and further into the problem. DT also allows you to do a co-simulation, which means that you can sort of iterate between your finite element solver and your fatigue calculation, so that you can update stress strain fields based on how material properties are evolving as as cycles accrue on the part. So those are things that we can do with DT. EIE is a tool that we use for managing lengthy road load histories, right? And what I mean by a road load is sometimes an organization will go out to the test track and they'll make measurements of the loads that go into a part. And of course, if you're driving down a bumpy road, you're going to end up with variable amplitude data, potentially on several channels, right? If typically in a rubber part, they'll look at 6 channels. You'll have 3 forces and 3 moments that go into the part, and so they'll just make recordings at, let's say, 1,000 hertz, right? And so if you have 1,000 hertz over a half an hour event at the track, that means you've got 2 million time steps of information that that you want to analyze. And if you try and take that 2 million time steps and directly feed it to a finite element model, it's not going to solve, because it'll just be too much information. But with the EIE tool, what we do is we can take the road load data and we can convert it into stress strain history to use in fatigue analysis. And it's an interpolation based method. So we pre-compute a small number of representative states of the part, and we interpolate between them to very rapidly generate strain history. What's nice about this is it does allow you to capture rubber's nonlinearity, and it's also extremely fast. It's like 10,000 times faster than running a finite element model. So very powerful tool, and yeah, those are the 3 things that we use. And here's kind of a chart that shows how these different workflows map onto the different levels of analysis depth. So if you're doing the infinite life approach, you're probably just going to stick with CL, because you're probably just going to calculate a safety factor. If you're doing safe life, maybe you'll use CL, because right, you can get repeats of a single load case, but sometimes you're going to want to get sometimes you're going to want to model what's called a block cycle schedule, which is, again, you sort of say, here's load case A, so many repeats, load case B, so many repeats. You specify that schedule, you run the part through that schedule, and at the end of it, you say, oh, it didn't break yet. How many repeats of the whole schedule can I run? So that's still a safe life type of thing, and you can do that with our incremental solver. With the damage solver, like I say, you can do this incremental style of analysis so that you can monitor the growth of defects in the part. You can also use DT to look at residual life in the part, right? So another type of problem is, hey, here's the history that's happened so far. If I assume that this is going to happen in the future, how long will it last? That's what we call residual life, right? And then finally, if you're trying to do a digital twin, then you want to do this with our DT and our EIE tools. And what's beautiful is these tools run fast enough, especially with EIE, they run fast enough that you can actually do this in real time these days. Okay, so that's kind of an outline of everything. Here are some of the scoping questions. As you're deciding which pieces of these you want to bring together, you're going to say, what's the implication of a failure, right? Because what you're looking to do is economically justify the activity that you're going to do. And so the first thing to say is, well, if this thing fails, what does that cost somebody, right? Sometimes if it's a little rubber grommet that fails, well, it's $1 part on a dollar problem and nobody cares. Other times we've had projects where there's a rubber part that's off in the middle of the ocean, and if it fails, they have to send a ship out to change the part. And if you can imagine sending a ship with a crew and all of the equipment it takes to change, you know, a rubber isolator on an oil platform, you're talking multi-millions of dollars. And you know, so that's one of the first questions to ask when you're trying to scope what is justifiable. You also want to think about opportunity costs. You know, which would be, you know, what's an example of that? It's like, you know, if we do this, maybe that opens a future possibility that has a lot of value that could be realized. And so, you know, sometimes opportunity costs are important to think about. Um, uh, you also need to think about the cost of a build and break development path. So if you don't do simulation, that means you're going to have to build and break. If it takes you 6 months and 10 people per iteration, there's a cost there that you need to think about. You know, is this a thing that's happening once, or is this a thing that's a product on a market that 1 million people are having? You know, you have to think about, a lot of times the scope is driven, by the requirements of the customer. So for example, if you work at a company that's a rubber part supplier, your customer is going to be the person who makes, or the company that makes the car. And the company that makes the car is going to come to you and is going to say, well, here's the test that your part must pass in order for us to buy that part, right? And so they're going to come with specs that you're going to have to pass, or maybe there's regulations. I know in the tire world, you're not allowed to sell a tire in the United States or in other places of the world unless you pass certain tests, right? There's a government testing standard, and you have to pass that standard in order to bring your product to market. And so a lot of times those kinds of things will help you to scope what kinds of activities need to happen. Availability and type of use case knowledge. How much do you know about how the part is used, right? If you know a lot about it, there's an opportunity to bring that knowledge to bear on predicting the life. If you don't know a lot, well, a simpler approach might be better, just because you don't have the information that it takes to feed a more sophisticated analysis. So sometimes that's a limit on what you're going to do. Anyhow, these are things you should always think about as you're trying to align your budget and your goals. So now what I want to show you are some concrete examples. So for the infinite life approach, I've chosen a rubber grommet. This is an example of a super cheap part, right? They're super cheap to mold. And if it breaks, well, you just put a new one in, no big deal. The guy who makes these parts, you know, these parts are sort of usually made by small manufacturers. They don't usually have a sophisticated analysis capability. And so when they come into this, they need answers really cheaply. And so Safe Life's a really good fit for these kinds of problems. Or excuse me, Infinite Life. Another part would be sway bar link. This is a component of an automotive suspension. And you know, the automotive OEMs will typically give you a target life that you need to hit. So Safe Life is where you're going to, what you're going to want to do here for a sway bar. A good example of the damage tolerant approach is in the tire specs. I mentioned there's government regulations when you sell tires. So there's a test called the FMVSS 119, and it's a test that tires have to pass. And it's not a test at a single load case. It's actually a composition of a series of load cases. And so yeah, so it's necessary to you know, be able to simulate that series of load cases and simulate how the damage evolves under those different load cases in order to check your tire design. And then finally, I want to show you an example of of what a digital twin could look like. It's kind of academic at this point, in the sense that we actually haven't sold that. I'd love to find a customer who wants to do it. A lot of people are talking about this these days. I think in the future we will see more digital twins coming, and we've built a prototype one that I'll show you here, but certainly possible to do. And the example I'll show you is for an automotive transmission mount. Okay, so talking about infinite life. So this is a picture of rubber's fatigue crack growth rate curve, right? On the high end, you have the strength of the material TC. On the low end, you have the fatigue limit T naught. And in between, you've got this green curve that controls for a given fracture mechanical energy release rate, what is the rate of growth of the crack. And now if you're in the infinite life approach, the only thing you need to know is this lower bound, right? I don't need to know anything about the rest of the curve. I just need to know that lower bound, and I need to make sure I'm below it. The way we do that is on the analysis side, we use an analysis method called critical plane analysis. And the idea in critical plane analysis is, because loads can be very complicated. You can have, right, if you have a stress tensor has 6 different components, and so as you're feeding loads into a part that are coming from multiple directions, the question is how does a crack on a particular plane experience those loads? And what you do is you resolve the stress tensor onto that specific plane, and you look at the history of the traction vector. And from that history of the traction vector, you can typically find, well, you can find what's the worst case. And what you can do is you can compare that worst case to the crack precursor size. So in the infinite life approach, what we do is we make this calculation of the traction vector on every plane. And then, like I said, we scan over every single possible plane, and we calculate a safety factor on every plane. And then the plane that gives you the smallest safety factor, that is the safety factor that we report as the safety factor of that particular element. And we do it for all the elements in a model, and that tells you whether your part is going to pass or fail that particular set of conditions, right? So this is just the critical plane search, scanning through different possible crack orientations. Once you've done that search, you can visualize the results as colors on a sphere. Each point on the sphere represents a unit vector that is the normal to some plane that represents the plane of a crack, and you can color the point on the sphere according to the safety factor, right? So small safety factors are colored as red, and then large safety factors are going to be colored as blue. So the place where the sphere is the most red, that's the safety factor that we take, and it also predicts the orientation of the most likely crack for that particular strain history. So here's my grommet example. In this case, we're going to model 2 loads. One is going to be at a low load, and one's going to be at a high load. We're just going to measure the stiffness of the rubber, the precursor size of the rubber, the fatigue limit of the rubber. We feed that into these calculations, and here's what you get. So this is an overlay. I've animated the part so you can see this is the load. This is the low load case. You can see there's sort of a rocking motion of the grommet. And I've colored the model according to the safety factor that's been computed with critical plane analysis. If you see red, that's a safety factor of 1.0. If you see black, that is where the safety factor is below 1, right? So that's not infinite life. Everywhere else is infinite life, and blue is a very large safety factor. Red is just on the line. In this case, under the low load, the worst element happens to end up with a safety factor of about 2.6. So we're going to have infinite life by a factor of, with a margin of about 2.6 in relative to the life limit. If I repeat the analysis for the high load case, now you can see I've jumped over the fatigue limit, and I've got a couple of elements here that are colored black, and those elements have a safety factor of 0.43. So this doesn't mean that the part has failed instantly, but it does mean that the life will not be infinite. And it doesn't tell you, this does not tell you how long the part will live. If we see the black elements, that means maybe we need to do the safe life approach, or redesign the loads or the part or something. Right, so that's a little bit about the infinite life approach. Here is the sway bar link. And we're going to do a safe life analysis on this. So here's an example of the material characterization we might do for this, right? So we have stress strain curves, we have fatigue crack growth rate curves, we have a crack nucleation curve. From these 3 pieces of information, we can computationally generate rubber's Hay diagram, which is a map showing how the fatigue life depends on the applied mean strain and the applied strain amplitude. That's the materials characterization that we would do. And if, for example, we wanted to model a uniaxial load, right? Since this is just a link, this link gets loaded uniaxially. So we can just look at the displacement history, maybe from a road load recording. Now, since these are road loads, we don't want to just feed this direct road load directly into the final element model, because that would just take way too long. What we're going to do instead is we're going to compute a map, right? So we're basically going to take the part, we're going to load it from 0 to 4 millimeters of displacement. And in this case, we're going to do that in about 8 increments. Those 8 increments of loading create a one-dimensional map of the relationship between stress strain fields in the part and force displacement input to the part. Once we have this map, the EIE tool can say, okay, for any point on this history, if I'm here, I'm just going to look at these 2 load cases and I'm going to interpolate between them, right? So then to generate this, I'm going to use my map. I'm going to sort of remix it, interpolate it, and then generate this big history. And I can use that for my fatigue analysis. And if I do that, I get, you know, some sort of life. These are life contours on the part under that road load history. In this case, we get a life. The failure is going to be near this inner metal contact point, and it's a life of about 30,000 repeats of that event at the track. So that's an example of a safe life analysis on the link. Here's an example from the tire world for the incremental analysis. This is the FMVSS procedure and the EC. By the way, there's 2 procedures here actually. The first is the FMVSS, which is if you want to sell a tire, you have to pass the first 4 steps, right? If it doesn't pass the first 4 steps, that tire is illegal in the United States. Now, in addition to those first 4 steps, there's a European test standard that tire companies use to assign a letter grade to a tire. If you buy a tire that has one of these letter grades at the end of the tire nomenclature, that is an indicator of what's called the speed rating of the tire, right? So if you have a Q speed rating, that means the tire was able to pass 160 kilometers an hour. If you have a Y speed rating, the tire will, is fine up to 300 kilometers an hour, right? You better be on the Autobahn for that one. But so the question is, can we model this? And yes, to do that though, we're going to need to use an incremental analysis where we say, okay, run this load case for 120 minutes, and then run this load case for 30 minutes, and this load case for 30 minutes, and so on, up until the tire lets go, right? When the tire lets go, that basically gives you your letter grade for the speed rating. And we can simulate that. Now, in order to simulate this, you definitely need to take into account all sorts of things. You need to take into account temperature dependence, in particular, because at high speeds, the tire will heat up significantly. So we need to model that heat buildup. We also need to model the temperature dependence of the crack growth rate law. This is a plot that shows the dependence of the strength of the rubber as a function of temperature. And this strength is one of the inputs to our crack growth rate law. So that lets us represent this thermal effect on the strength of the rubber in a tire. And now these are pictures of the tire model at different speeds, ranging from 80 kilometers an hour, right? There's one of these images for each of the steps in the schedule that I showed you earlier. And what you can see here is up to about 200 kilometers an hour. It's kind of boring. There's some modest, changes in the solution. But once you hit about 210 kilometers an hour, you start to have some really interesting dynamics, because in a tire, you get what's called a standing wave, where the rotation speed of the tire corresponds to some natural frequencies in the structure. And you actually, at steady state, get these standing waves, very destructive to the tire, because, prior to a standing wave, you really have one deformation cycle per tire revolution. Once you get a standing wave, you get multiple cycles of the rubber per revolution of the tire. Very damaging, and this is where you'll see a large amount of self-heating. So this is a picture of the calculated temperature as a function of the step in the test. So you get the standing wave right here at about step 10 is where it starts, and then you can see the temperature just shoots way up in these tests. These are contour plots showing the temperature. Here we're comparing on a drum, doing the test on a curved drum versus on a flat road. The drum is more severe, and we can predict that with our models. This is the workflow, and I don't dare try to explain it. You know, the incremental workflow does get a little bit complicated because you're kind of starting and stopping. You're saying, well, do damage for this step, and then take the damage state of the tire and do another step, and that you know, the end of that step becomes the beginning of this step, and you know, bring all the temperatures in, and it gets intricate, but it can be done is the point. And here's kind of the final result when we follow that workflow. What we get is a plot of residual life as a function of time into the sequence of tests in that schedule for the FMVSS and for the speed ratings, right? So if you survive for the first, what is that, 13,000 seconds, that means you've passed the FMVSS 139, and then you can see these are the points where you pass the Q, the R, the S, the T. Now in this case, these models were failing at the H and V speed steps in the procedure. Interesting, you know, prediction of speed ratings in tires using our fatigue technology. Last example for the fail-safe approach. This is an example where we've implemented a digital twin of the of a transmission mount, automotive transmission mount. And the way the twin works is basically you have a car and a data acquisition system that's measuring force and displacement inputs to the transmission mount. We're going to take we're going to use EIE, right? This tool that interpolates loads. We're going to take those real-time loads, and in real time, we're going to convert them into strain history. And then we're going to use the incremental solver to take that strain history and say, okay, over this 1 minute of strain history, how much damage happened? We're going to update the damage state of the model, right? We're going to accrue the actual damage, and then we're going to do a second calculation. We're going to say, okay, since I've accrued this much damage, what does that mean in terms of change to the residual life under some hypothetical, right? If we say we measure the life of the part in terms of 100% load, we can compute the residual life. So we do these two calculations in real time, and then we update a dashboard where I show, you know, maybe a driver or a fleet manager, hey, here's what the damage on your part looks like. And now, of course, this all happens, you know, this basically happens on a periodic, so every minute or every hour, you update this calculation loop. And so you basically have a running dashboard of the state of your part. And if somewhere you get, you know, accrue enough damage that the part is going to fail, you know, tomorrow or next week, you can send an email to somebody and say, you know, change that part out. So that's an example of a predictive maintenance system or a digital twin. And so now, in order to use EIE, first we have to pre-compute the solutions that we use for interpolation. So this is a picture of a final model going through the motions that are used to pre-compute the interpolation grid, right? So basically you make a model of the mount and you run it through every possible deformation state that might happen in the application, and that's your map. Now that's a thing that you do before you get to the field and start operating the twin. Once you've done that, then you're ready to go ahead and start the twin. I guess the other thing we need to do is so first of all, we have to pre-compute the map. Second of all, we have to initialize the residual life, right? So how do you measure residual life? Well, you pick a standard load case and you say we're going to measure residual life in terms of repeats of the standard load case. So the first thing we're going to do before we accrue any history, we're going to say what is the fatigue life of the standard load case before we've accrued any history. So we need to initialize that before we start the twin up. And this is a contour plot showing the fatigue life on the mount of a load case where we're just doing vertical vibrations, right? We assume the major thing going on are these vertical vibrations. So that we've initialized that, now we can get in. This is the another detail on that map, right? So to compute the map, we just look at all the possible load states. And then this is where we get into the twin demo. And I think I'm getting close to the end of my time, so I'm not going to actually run this thing because it takes a couple minutes. But if you're interested, go to the Endurica YouTube channel and look up Digital Twin, and you'll find this demo on our YouTube channel. Basically, we feed in real-time loads, and this map of damage updates in real time as we feed in snippets of loading. So you can see that, and you can see the computational requirements of the twin prototype. So yeah, so these are the approach, and you can see that we've gone from very simple to very sophisticated, and hopefully you can find something that matches what you need to do. So I will stop there and open up for any questions or discussion that you guys may want to have.
Perfect. Thank you so much, Dr. Mars. Excellent presentation. I personally loved it because my mindset is all about metals and alloys. Very informative to me. I guess I learned a lot. Thank you so much. I have a couple of questions which I can ask at the end. I let the students and other faculties, if you have any question, please feel free to ask, because I do not yet see the questions here. I don't know.
I
Hussein,
see.
do you see
Thank you very
something?
much, Will. Mason, I see some questions.
Okay, go ahead, please. I
Um,
can't see them. Go ahead.
Yes. Thank you very much, Will. Very interesting talk. I have a couple of questions, but can wait for the end. So
Yeah, okay.
Bilal has a question, and it is, when you talk about all possible loads, how are you defining the boundary condition? In particular, how are you defining the movement of the rod?
Yes, in the case of that transmission mount, in the case of this transmission mount, this is all under displacement control. Now, this very much depends on the application. These tools will allow you to do it in displacement control or force control, or if you want to mix and match, if you want to have one channel be displacement and one channel be force, that's fine too. But I guess the important thing is that what you do in your finite element model should match up with the inputs that you're getting from your data acquisition system. So if you're measuring displacements, then you want your finite model to be displacement based. If you're doing forces, you want to use forces. Um, in this case, the mount is fixed on one end. You can see it's glued on the bottom, and then the that rod is basically treated as a rigid body. It's tied to a single control node through which we input X, Y, Z, displacements. Good question.
Okay, and thanks. And a follow-up question. Also, are those jobs explicit or implicit?
In this particular case, this was implicit. We support both paths. We've done. In fact, I've got another really interesting work that we did with tires using a combination of implicit and explicit. So we used implicit to model steady state rolling on a tire, and then we used explicit to model the impact of the tire with an obstacle. And you can combine these things to look at the bruising or the damage that accrues in the tire because of the impact with a curb or whatever. I didn't show that here, but that's another application. That'd be a whole nother hour to unpack that one. But yeah, you can use both, either or both, implicit or explicit.
Thank you. So I guess I have a question from Kareem. He's asking, does the strain rate have any effect on the fatigue behavior of rubber materials? Because it shows that a big change in strain rate can influence on fatigue properties of some metals.
So Um, for rubber, so, definitely. So this is one of those tricky questions because definitely at a high level, rubber can be very rate dependent. Um, and I put an asterisk on that because there are also a lot of problems where the rate dependence is not so important. So the question becomes, well, when is it important to think about rate dependence? And the answer to that is if the rubber is operating near its glass transition in terms of, so if you know polymer science, right, if you plot the stiffness of the rubber as a function of temperature or as a function of rate, all polymeric materials go through what's called a glass transition. If, at cold temperatures and at very high rates, the material can become much, much stiffer, like 10,000 times stiffer. And that's when like an engineering plastic is an example of material that's below the glass transition. Above the glass transition, that's what we normally think of as a rubber, right? When you're on the high end of the temperature or the low end of the frequency, then that means you're well above the glass transition. Um, and that's called the rubbery plateau. If you're on the rubbery plateau, and if your change in rate is, let's say, less than a decade or 1.5 decades, then rate effects probably don't matter. If you are close to that glass transition, then your rubber will be extremely rate sensitive. So that's the main thing to think about. If someone says, let's do rate dependence, that's the first thing to ask is, where's the glass transition and where am I relative to that? Good question.
Um, and Bilal, sorry, has another question. Thank you. Well, is there a reason why you're using the tet mesh as opposed to hex?
Yeah, because it's easier.
That was a simple answer. Well, while I have most of the audience and students here, there are some thank yous to the questions and answers. Well, I basically had a general question. I have like technical question as well, but I wanted to ask this while the audience are here, mostly for the benefit of the graduate students. You work in basically corporate and companies, and then you switch to this career. So I was basically wondering if you can share some of your experiences in terms of pros and cons of basically working in each of these environments. And what was it like for you to go through these transitions? And what are the things that you learned that you might be able to share with our grad students who are thinking about a career, basically future career for themselves?
I would say that my career has been very curiosity driven and very sort of what making sure that I like what I do. I don't know. That sounds kind of cliche, and in some ways it's not. In some ways it's not true that just because you like something it ought to work out. That's definitely not always true. Um, uh, on the other hand, when I in the corporate, what I loved about, I would have been happy to stay on the corporate side, for a long time, but when the opportunity to do this kind of presented itself, it was a very interesting question because, in a corporation, um, I was in a research group, and yeah, you, I guess the nice thing about work on the corporate side is that if you're in the researcher position, you don't necessarily have to worry about how your work is funded. Your manager does that, right? Um, and so if you don't want to think about that, that's a great place to do it. And you can focus on let's say technical excellence and on on that side of it. Now, I have to say that when this opportunity presented itself, to be honest, I had no clue what it would be like to be in business for myself, or what it would take to create this kind of thing. And it's been, if you've ever watched, there's a movie, Lord of the Rings, where Frodo carries a ring to the mountain and drops it in the lava. That's kind of like what starting a business is. So if you're not up for that level of drama and intensity, starting a business might not be for you. But the very rewarding thing is that in a small business, and I would say, I guess one piece of advice I would say is don't be afraid to work for a small business. Of course, in large corporate research, there's a lot of I guess the nice thing about large corporate research is it's well funded, and so you can do a lot of really cool things. On the other hand, you'll find that a lot of times in larger organizations, you will find your activity is much more constrained by whereas in a small organization, there's a lot more freedom. And now, obviously, you have to, what you do has to, in a small organization, there's more freedom to respond to economically opportunities. Let's say it's not freedom to do whatever you want. That's not the same thing. But if you see an opportunity in small business, you can pivot. You can leverage it. If you know how to solve a problem that no one else solves in a small business, you can do it just like that. Whereas in a corporate environment, your good idea may or may not fit into the grand scheme of things, and you're going to be subject to the constraints of the organization around you, which, like, I'm not saying that's a bad thing. It's a good thing. Our economy creates really magical things through big organizations. But it is a very different environment. In some ways, it's a little bit like the difference between living in a big city or living out in the country. It's like in the big city, there are a lot of constraints on what you can do in your yard, right? If you live out in the country, you're allowed to have bonfires, and you can do whatever you want, but
Yep.
your crops better not fail.
Yeah, thank you very much. And I want to basically add one comment there for our grad students looking for jobs. Unlike Northeastern California, here people aren't looking at opportunities in small businesses such as startups, but a lot of things that Will mentioned, they're there. So there are flexibilities, possibility of getting things done, and if your work is successful, your company is successful in terms of the reward, simply financial things, it's going to be very much different than working in big corporate. So I would encourage everybody to keep an eye out for those opportunities that are more popular in Northeastern California than here. They exist here, as we see in a relatively small city. Will has been successful doing this basically small business.
I would say the most important thing is just make sure, and this applies no matter where you are. The most important thing is make sure that you're working on problems that matter. If you don't think that what you're working on matters, then go do something else. But if you've got a problem that you're solving that somebody needs solved, you're going to do fine wherever you are. So.
Thank you. Before I turn to Maysam, to you, I just want to apologize. I didn't read properly. The name of the student asked the question was not Karim, it was Kameen. So just want to correct that and apologize. So Maysam?
Okay, again, thank you so much. Again, I just add one quick note here that really is, I guess, a great example of one of the successful alumni of UT, and in particular, Laboratory of Fatigue. I remember I talked to Dr. Fatemi once, and he, in particular, used your name as a very successful alumni in his research lab. I have some questions, but I postpone most of them when we meet each other in person. I just ask one question, and again, if this question doesn't make sense to you, let me know, because my mindset is still on alloys and metals. My question is about the physics of fatigue in rubbers. What would be the mechanisms of crack initiation when we talk about fatigue of rubbers? Because in metals is all about dislocation, slip activities, defects, internal defects, surface defects. What about, I'm really curious, what happens in terms of crack nucleation in rubbers?
Well, first of all, rubber is in no way, rubber is in no way a a crystalline material. I know I said that there is a strain crystallization effect. In rubber, what crystallization means is that you have millions of nanoscopic crystals. It doesn't mean that you have one big grain or anything like that. So, so rubber is a very amorphous type of thing. If you look at it under the microscope, it does have a lot of microstructure. That microstructure is imparted by several things that are in the recipe of the rubber. So for example, natural rubber is an agricultural product, right? They harvest it from trees in Southeast Asia. And since it's an agricultural product, that means that the rubber has a certain, it's a small fraction, but it does have a certain fraction of contaminants in it, like bugs and dirt and twigs. They get ground up, but there are microscopic, inclusions in the rubber that can serve as crack precursors. Also, typically rubber is formulated with fillers. Like they use a material called carbon black. It's a particulate thing that they put into the rubber, makes it much stiffer. But if the carbon black is poorly dispersed in the rubber, that also can create sites where you have crack starters. And there are also particulate ingredients like the zinc oxide in the cure system of the rubber. Depending on the mesh of particle they use for that, those can also be crack precursors. So there's a bunch of populations of microscopic things that potentially can serve as crack initiators in rubber. And so it's always a game of, well, which ones are the worst? And if I start controlling those, then what's the next worst? And that's the game that we always play.
Sure, perfect. Thank you so much. As I said, I have some more questions, but I postpone it when we meet in person. And hereby, I officially invite you to come to our lab, see new changes, new equipment. Could be interesting to you. So hopefully sometime in summer, once all this COVID stuff is gone, we can meet in person. I see Dr. Alahinia's camera is on. Dr. Alahinia, if you have any final questions, feel free to ask, please.
Sure. I was going to thank Will for the interesting presentation. One question is, have you applied this methodology and your model to materials that may not necessarily be rubber, but have some super, maybe plastic or super elastic behavior at all?
The answer to that is sometimes people do ask us to do that kind of thing. We're always a little bit trepidatious about it. I think the overall framework is a good framework for looking at all sorts of nonlinear behaviors beyond just rubber. We have looked at TPEs, right, thermoplastic elastomers, which is kind of maybe a half plastic, half rubber type of material. We've done quite a bit of work with those actually. In fact, we've got a project right now that's looking at a material that's very plasticky. It's in the solar industry. I'm not allowed to say what it is, but that material is probably more plasticky than rubbery. There are some unique issues in plastics that we haven't really dealt with well yet, specifically plasticity, right? If you have large yielding in the material, our methods start to not be great. And we are, like I say, we do have a great interest in, well, how could we develop capabilities in that direction? But another category of material that we've done a little bit with is foams. Open cell or closed cell foams. So we get that request a couple times a year, and we've done a little bit with it. Again, foams often are modeled as hyperelastic things, and so our framework works very well for foams. Although foams are different because whereas most rubbers are incompressible, foams obviously, can undergo very large volume changes. Yeah, those are some of the other materials we've worked on.
Thank you. Hopefully, when you get to visit Maysam's lab, we can discuss more.
That would be
Thank you.
great. Thank you so much for the opportunity. It's really fun to come back and say hi to everybody and see how the school is developing. And
Yeah, but
Yeah.
I will send you. Yeah, I will send you an email for some follow-ups, and we can set up a time for sure.
That would be great. Maysam, I have
Dr.
one last thing, sorry,
Sure. Go ahead. Go
before
ahead.
we wrap up. So, Will, the question was asked about any potential openings in Endurica. I don't know the answer to that. What is the answer to that? But in general, we would
Co-op
appreciate
opportunity.
if you share any
we
opportunities with our
we
students.
we do hire co-op students. And this summer we've got this summer we've already got our this summer is basically already full up for co-op students. For terms after this summer, we definitely would be interested to, you know, have people in on an internship type basis. And I will say that there are not as of today, but probably later this year. And certainly next year, there are going to be, so Endurica is growing at about 20% a year right now. And so we do expect to be hiring more people. The kinds of things that we'll probably be looking for will be things like, probably pre-sales types of roles where, you know, we're looking for people who know how to take our technology and be persuasive and know how to take it to somebody and show them how it can help them. And there will be more. We'll be looking for people who can help us, support a larger user base. We get people who call with questions on how do I do this and how do I do that, and like I say, we will be hiring. I mean, we're not a Fortune 500 company. We're not going to hire armies of people, but over the next 2 years, it's certainly possible that we would hire 1, 2, 3 people in, like I say, pre-sales types of things and tech support types of things.
Thank you. Thank you.
Yep.
Okay, Dr. Sujudi, any other question from audience? Because I don't see anything on my end. If there is no other
that's
question,
it.
I have nothing to add except, again, thanking the speaker.
Yep, we can conclude here. Thank you very much.
Thank you so much, Bill. And as I mentioned, hopefully we see you early in summer. We plan, I send you an email and we can do some follow-ups.
That would be great. I need to get out of my dining room.
Thank you so much. Enjoy your long weekend, everyone.
All right, you too. Bye-bye.
Thanks. Bye for now.